let us continue our discussion on how to apply Laplace transform to solve some simple yet practical problems. So this is a problem for us. We have a series RLC circuit, resistance, inductance, capacitance in series with a battery of EMF E, and there is a switch which was open, but then at time t equal to 0 this switch is suddenly closed. Now this is given that the voltage across the capacitor Vc before this switch was closed, that is at time 0 minus, was equal to 0, and the question is to find Vct for time greater than equal to 0. That means after this switch is closed. We will use Laplace transform to solve this problem, but before that let us spend a few moments in guessing what will happen physically. So before the switch was closed, there was no voltage across this capacitor or no stored charge in this capacitor. There was no current flowing in this loop because the switch was open. Then the moment when you close this switch, we get a closed path. Here the voltage across the capacitor is 0, but this voltage across the battery is E. Therefore, we will get a current I which will start to flow when you connect the switch, when you close the switch. However, this current I cannot pick up a finite value instantaneously because we have an inductor in series, and for this current to change rapidly from 0 to a finite value, then L di dt will be infinite, so that will require infinite voltage across this inductor, so that is not possible. That means the current cannot become non-zero, finite suddenly at this moment like this. That is not possible. So current will increase gradually, and as currents continue to flow, so this is our current versus time graph. Let me also plot time versus capacitor voltage. As current continues to flow, we will get some charge stored here across the capacitor plates. So capacitor voltage will also increase, and it will keep increasing until this voltage equals the battery voltage E at some point of time. Then this voltage are equal, so you may say that this current should stop at that point. However, the current cannot stop instantaneously because of this inductor. Inductors do not allow currents to change instantaneously. So current will continue to flow even after this point when the capacitor voltage is equal to battery voltage. So this current will keep on flowing in the same direction, and therefore this capacitor voltage will increase. And when this voltage becomes larger than battery voltage, then this side has larger voltage, so that will try to stop this current or reduce this current. So then this current will gradually decrease from the moment after this capacitor voltage is more than the battery voltage. Then this current will start to decrease, and by the time this current becomes 0, this capacitor got overcharged, and then this current will be 0, but this capacitor voltage is now more, and therefore the current will start to flow in the opposite direction, or this capacitor will start to discharge. So then current will reverse its direction, and capacitor voltage will start to come down, and in this way it is possible that the capacitor voltage will come down again below this battery voltage E, and in this way there may be an oscillation of current from left to right, right to left, and also this capacitor voltage can oscillate. It may get overcharged, and then it will discharge, and may get undercharged, and this capacitor voltage may also oscillate like this. But finally, after some time, after sufficient amount of time, when everything settles down, then we can say that, if everything settles down, then definitely this capacitor voltage will be equal to this battery voltage E at that point. So this will come down and settle to this battery voltage, and also this current will stop at that point. So before that this current may oscillate, but finally it will become 0. That is what our intuition tells us. Now we have to see whether we get similar interpretation when we use mathematics, when we use Laplace transform. So let us do the mathematics. For that, let me call the voltage across this resistance as VR, function of time, and let me take my reference polarity as left side positive, right side negative, and the voltage across the inductor is VL as a function of time. Left side positive, right side negative is my reference polarity, and capacitor voltage VCT with reference polarity as upside plus, downside minus, and the current from left to right is IT. Now consider this loop, and let us write KVL in this loop, Kirchhoff's voltage law. So we can write the sum of these three voltages, VRT plus VLT plus VCT, equal to this supply voltage E, okay, which is constant. Now we can write that VLT, this inductor voltage, is equal to L di dt according to the chosen direction of current and chosen polarity of voltage. In the same way, for the capacitor I can write this current, this is IT will be equal to C dVc dt, again according to the chosen direction of current and polarity of voltage. So therefore from here we can write VR is equal to R times IT, this current and resistance, Ohm's law. Then VL, that is L di dt, plus Vc, let me keep it as it is, and this is equal to E. Now in place of I, let me put this C dVc dt plus L d, in place of I will write now this, so it will become L C second derivative of Vc, okay, plus Vc as it is, this is equal to E. I am writing this differential equation in terms of capacitor voltage Vc because in the question it is asked to find Vc. Otherwise, if you want, you can write this differential equation say in terms of current IT as well. Next, let me rearrange the terms in this way. The second derivative first, then I will write this first derivative, and I will divide by LC this entire equation. So the coefficient of second derivative will become 1, this coefficient will become R by L, plus here we will get 1 over LC Vc, this is equal to E divided by LC. So now we have a differential equation second order, so we can solve it, but we will need two initial conditions. One of them is already given in the question, Vc 0 minus is 0, but we need 2, but the other one we can write in this way, that dVc dt at time t equal to 0 minus, that is nothing but from here it is I0 minus divided by C, and I0 minus is 0 because when the switch was open no current was flowing, so I0 minus was 0, therefore the first derivative of this capacitor voltage is also 0 at time 0 minus. This was not given directly in the question, but this is easy to understand. Okay, now let us solve this. For that, let me take the one-sided Laplace transform of all these signals. So we will have this multiplied with step signal plus R by L, Laplace transform of this term multiplied with step signal plus 1 by LC, Laplace transform of Vc TUT, and right side is this constant, then Laplace transform of ut, which is 1 by s. Let me write it. This is equal to E by LCS. Now, here we have three terms, 1, 2 and 3. Let me start from this third term. Let me write this as 1 by LC capital VCS. That is the unilateral Laplace transform of VC. Okay, this term. If so, then this can be written as R by L multiplied with VCS minus VC at time 0 minus. And then this first term will be S square capital VCS minus S VC0 minus and minus VC dot 0 minus. Okay, where VCS is the unilateral Laplace transform of VCT. Now this is equal to 0, this is also equal to 0, this is also equal to 0. Therefore we can write, by taking VC common, S square plus R by Ls plus 1 by Lc is equal to, the right side is here, E by LCS. Okay, then VCS is equal to E by LC, and let me write 1 over S multiplied with S square plus R by Ls plus 1 by Lc. Now to get the capacitor voltage as a function of time, you have to take Laplace inverse of this by using partial fraction. But one important thing is that, see, this is a second order term which is coming from a second order differential equation like this, and we get similar second order differential equations in many different situations. Therefore there are some standard way of writing this, okay, so that you can apply the same knowledge, same trick in different similar problems. So we will learn that now. So for that, let me define this term 1 by Lc as 1 by Lc is equal to omega n squared, okay, which means omega n is equal to 1 by root Lc. Then this coefficient R by L, which is also here, R by L, I will write it as 2 rho omega n. So that means rho is equal to R by 2L, R by 2L, okay, divided by omega n. So omega n is here, so root over Lc. So this is equal to R root C by 2 root L. Okay, so these are the definitions I will use, and therefore Cs is equal to E by LC 1 over S, and this will be S square plus 2 rho omega n S plus omega n square. This is a standard form of writing a second order term in this way. Then we will write 1 by S, and this we will write as S plus rho omega n squared, okay, then minus, so we are getting S square, we are getting 2 rho omega n S this term, but here we are getting an extra rho square omega n square, so we will subtract that rho square omega n square, and then this omega n square as it is. You may also take these two terms together and write as omega n square 1 minus rho square plus. Now let us try to do a partial fraction. You can do it in many different ways. Let me do it in this way. A divided by S plus B plus CS divided by this quadratic term, S square plus 2 rho omega n S plus omega n square. Okay, now that means if you cross multiply and add, you will get here inside bracket AS square plus CS square, A plus CS square, okay, and then A 2 rho omega n S plus BS, so A 2 rho omega n S plus BS, and then plus A omega n square. Okay, this will be the numerator if you add these two terms, but the numerator should be equal to 1. Okay, so this should be equal to 1. So from this we can write A is equal to 1 over omega n squared, right, and then this term should be 0, so that means B should be equal to minus of this, so minus 2 rho omega n multiplied with A is 1 over omega n square, that is minus 2 rho by omega n, correct? Okay, then C should be minus A. C is equal to minus 1 by omega n square. Therefore, from here we can write VCS is equal to E by LC, then 1 by omega n squared, that is A divided by S, plus B is here minus 2 rho by omega n plus Cs, that is minus 1 by omega n squared S whole divided by this, and this is also same as this. Okay, so let me write in this way: S plus rho omega n whole squared plus omega n squared multiplied with 1 minus rho squared. This. Okay, this 2 minus you can take outside. Now it is easy to take Laplace inverse. So VCT will be equal to Laplace inverse of this, that is this constant E divided by LC. Then Laplace inverse of this term is 1 by omega n squared constant multiplied with ut because of this 1 over s. Then minus, now this term will give us sine and cosine signals. Okay, and because s is added with this rho omega n, we will also get e to the power minus rho omega n term. Okay, let me adjust this slightly. Let me write the denominator as it is. And here we have s, but I want to write in terms of s plus rho omega n. Okay, here we have s multiplied with 1 by omega n square, but I have added this extra rho omega n, so I will subtract this rho omega n by omega n square, that is rho by omega n. Okay, so this plus this is this term, and we already have this 2 rho by omega n, so plus 2 rho by omega n. Okay, now these two you may write together as minus 1 plus 2 is equal to plus 1, and erase this. Everything I am doing is just to write this in the form of a standard Laplace transform formula which is known to us. This is a bit of art that you will gain with practice. Okay, so now consider this term. Okay, so that will give us a cosine term with this constant 1 over omega n squared constant, cosine root over this term, so that is omega n root over 1 minus rho squared. Okay, cosine this multiplied with t, e to the power this term minus rho omega n t, okay, whole multiplied with ut. Then consider this term. Okay, from that the Laplace transform of this is this minus, then rho by omega n constant sine root over this, that is omega n root over 1 minus rho square t e to the power minus rho omega n e to the power minus rho omega n t divided by the root over this term which is omega n root over 1 minus rho square and then ut, right? Okay, now here you see that 1 by LC is equal to omega n square. So in place of this 1 by LC we can put omega n square, and then that will cancel with this omega n squares here omega n and squared, so this will cancel with LC. Okay, then this is equal to E. I will take ut common, so I will write 1 minus this cosine omega n root over 1 minus rho square t. This e to the power term I will write later. Then I will write the sine term with the coefficient rho by 1 minus rho square, rho by 1 root over 1 minus rho square sine omega n root over 1 minus rho square t. Okay, this 2 minus I will take common, plus this e to the power term is also common, e to the power minus rho omega n t, and this ut outside. Next, let us write this as E 1 minus, let me take 1 over 1 minus rho square common, then we have root over 1 minus rho square cosine omega n root over 1 minus rho square t plus rho sine omega n 1 minus rho square t, and this is multiplied with e to the power minus rho omega n t ut common. Now if you define this term as cosine theta and this term as sine theta, then this is equal to 1 minus 1 over 1 minus rho square. This will be cosine omega n 1 minus rho square t minus theta, then e to the power minus rho omega n t ut, where we have taken this as cos theta, this as sin theta, so theta is equal to tan inverse rho by this. Okay, so now we can plot this function as a function of time. Time versus capacitor voltage. So you see that when time tends to infinity, this term will be 0, so this part will be gone, only 1 will remain. So at t tending to infinity, the final voltage will be E. Okay, suppose this point is E. So this is time 0. After sufficiently long time, the capacitor voltage will be equal to E. That is nothing but this battery voltage. That is natural. After sufficiently long time, this battery and capacitor will have same voltage and this current will stop. That is the steady state. So final voltage at sufficiently large amount of time will be E. But before that, at the beginning, we have this star. Okay, so you see we have e to the power rho omega n t minus. So that is a term exponentially decaying like this. Then this is multiplied with a cosine signal. Okay, so this is something like this. Now when you multiply this cosine and this exponential signal, you will get maybe something like this. And there is some constant here. Okay, and then you have to subtract this. So that will possibly look like this. When you multiply this minus 1 by 1 minus rho square. So this signal is minus E divided by 1 minus rho square cosine omega n 1 minus rho square t minus theta. Now notice one thing. What is the value of this at time tending to 0 or 0 plus? Okay, so if you want Vc 0 plus, that will be equal to E, then 1 minus 1 by this factor, and this will be 1 when t is 0. This will be cosine minus theta. Okay, now tan theta is rho by root over 1 minus rho square. That means sec square theta equal to tan square theta plus 1, that is rho square by 1 minus rho square plus 1, that is 1 by 1 minus rho square. So cos theta is root over 1 minus rho square, and then this is equal to 0. Okay, so that means this part, okay, this part here to here together with E, that value at time 0 is minus E. So this point is minus E, and then when you add this with this plus E, the resultant curve will be like this. starting from 0, it will go up like this, and then it will oscillate for a while. Finally, it will settle down to the value of E, that is the battery voltage. Okay, so this is VCT. Now you should analyze this result. For example, what happens if the value of rho is small or large? If value of rho is small, then this exponential term will decay slowly, and therefore this oscillation will last for a longer time. And value of rho is here. Value of rho is given by this. Now if this resistance is smaller, then rho is smaller, and then oscillation will last longer. Physically, that is because if R is smaller in this circuit, then it will not dissipate energy much, and therefore this capacitor and inductor will continue to exchange energy between them for a longer time. Okay, then if this rho is large, then this oscillation will decay down faster. But if the value of rho is greater than 1, then this part will be complex, so we will not be able to visualize this signal. In that case, when rho is larger than 1, we will not solve it in this way. Okay, so this solution is fine when rho is less than equal to 1, or rho square is less than equal to 1. Okay, otherwise we will solve it differently. So let me start from here. This is VCS, okay, and in case rho square is greater than 1, we will write this as minus here, and rho square minus 1. Same thing, but now this term inside bracket is positive. Okay, so this term is positive, and therefore this is equal to E by LC 1 over S, and then this we will factorize as S plus rho omega n, this term, minus this term, minus omega n root over rho square minus 1 multiplied with S plus rho omega n plus omega n root over rho square minus 1. Okay, so this is A minus B, A plus B equal to A square minus B square formula. Okay, next we will apply partial fraction. Suppose this is equal to something by S plus something by this factor S plus rho omega n minus omega n root over rho square minus 1 plus something divided by s plus rho omega n plus omega n root over rho square minus 1. Now we have to find out the values of A, B and C. So this is equal to this. Now if you multiply the entire thing with this denominator, you can write 1 equal to A multiplied with these two terms, s plus rho omega n minus omega n root over rho square minus 1. Then this other term is plus rho omega n plus omega n root over rho square minus 1. Then plus b multiplied with s and this term s plus rho omega n plus omega n root over rho square minus 1 plus c multiplied with this s and s, this term s plus rho omega n minus omega n root over rho square minus 1. Now this is an identity, so this is true for all values of s. So if we put s equal to 0, then we have 1 is equal to a multiplied with these two terms, that is that if you multiply, you will get rho square omega n squared minus omega n squared rho square minus 1. This is equal to a omega n squared. So from this, a comes out to be 1 over omega n squared. Okay, next let me put s equal to, say minus of this, so that this term becomes 0. So s equal to minus rho omega n plus omega n rho square minus 1. Then we will have 1 equal to, this term will be 0 plus b is b into this minus rho omega n plus omega n root over rho square minus 1. Okay, and plus multiplied with this s plus this. So s plus this is 2 omega n rho square minus 1 plus c is, this term will be 0. Okay, so from this b is equal to 1 over this entire thing, which you can write as 2 omega n squared. Then if you multiply this, you will have rho square minus 1 and minus rho square minus 1 under root. Okay, now in the same way, let me now make this term 0 by choosing s to be negative of this. Okay, so next we will put s equal to minus rho omega n minus omega n root over rho square minus 1. Then that will imply 1 equal to this a term will be 0, 1 equal to 0 plus this B term will also be 0, and we will have Cs into this term. So we will have C S is this, so let me write minus here rho omega n plus omega n root rho square minus 1, okay, and then this is multiplied with S plus this, okay, and S is here, so this cancels. We will have minus 2 omega n root over rho square minus 1. This minus becomes plus. From this, C is equal to 1 over 2 omega n squared, then here inside you will have rho square minus 1 plus rho into rho square minus 1. Okay, and notice that since rho square is greater than 1, as we have considered here, all these coefficients C, B and of course A, they are all real numbers. Okay, so then we can write from here this is VC S, and the values of A, B and C are determined as above. C, B, A. Okay, so now you can take the Laplace inverse VCT, and that will be this constant E by LC. Laplace inverse of this will be A ut plus B. This will be e to the power minus this factor, this term, minus rho omega n minus omega n root over rho square minus 1 multiplied with t whole multiplied with ut, plus Laplace inverse of this term, that is c e to the power minus rho omega n plus omega n root over rho square minus 1 t ut. Okay, so this is the answer when rho square is greater than 1. Okay, now you can plot this signal as a function of time. So we have firstly e to the power minus something multiplied with t. You can check that this number inside the bracket is positive. Therefore, when t tends to infinity, this term will vanish. Similarly, this term will also vanish. Only this a term will remain. Okay, and if you put the value of a is here 1 by omega n square. Then this LC and omega n square will cancel, only this E will remain. So therefore, at very large value of time t tending to infinity, this voltage will again be the same as the battery voltage. Okay, now at t tending to 0, 0 plus, if you put 0 plus here, 0 plus here, you will get B plus C, and you verify that the initial voltage comes out to be 0. Okay, that is your homework, and then you have to draw this signal. It will look somewhat like this maybe. Okay, draw these two exponential signals, add them, add that with this constant and draw it. That is homework. And notice that in this case there won't be any oscillation as such. There won't be any overshoot or overcharging of the capacitor, undercharging, etc. So this voltage changes smoothly, quite smoothly compared to the case when the value of rho square is less than 1. Okay, now we have more homeworks for you. Firstly, draw and analyze these voltage waveform for various ranges of values of rho and omega n. That means basically the values of R, L and C. So let me just give you some hints. So this is the waveform when rho square is less than 1. Now this pattern is oscillatory. We call this underdamped pattern. Okay, and if you increase the value of rho, then this oscillation will die down faster, or we say it will damp faster. Rho is called the damping coefficient, and if rho is very small, then this oscillation will sustain longer. Particularly if you take rho to be 0, then this exponential decaying term is not there. You will have a cosine term oscillating forever. We call that undamped response. That means no damping at all, and in that case this term will have a frequency of omega n, because rho will be 0. Then this oscillation frequency will be omega n. We call omega n as undamped natural frequency. That is the frequency at which this oscillates when damping or rho is 0. Let me write this for you. Rho is called the damping coefficient. Okay, larger rho means less oscillation. If you take rho equal to 0, that means oscillation forever. And that will be with a frequency of omega n. Omega n is called the undamped natural frequency. That is the frequency at which it oscillates when rho is 0. Okay, and rho 0 means essentially the resistance in the circuit. The resistance in the circuit will be 0. Okay, when rho is 0. So there will be no energy loss in the resistance, and the oscillation will sustain forever. And then this term omega n root over 1 minus rho square, this term, this is called damped frequency. That is the frequency at which this oscillates when rho is non-zero. Okay, let me write omega n into 1 minus rho square. This is called omega d, or damped frequency, the angular frequency to be precise. Okay, and then as we said, rho square less than 1 means oscillation, which we say as under damped response. Okay, and if rho square is greater than 1, then that case is here. There is no oscillation at all. This is called over damped response. Without any oscillation. Now rho equal to 0, that is one extreme case, then that is called completely undamped response. That means, as we already said, infinite oscillation. I mean, oscillation will never stop. Okay, and then if you consider rho equal to 1, that is the boundary between underdamped and overdamped situation, that we call the critical damping. Here we will not have any oscillation, so let us come here. If rho is 1, then this will be 0, so cosine term will be ineffective, so there won't be any oscillation. That is the boundary case. Also here you may put rho equal to 1, then also you will see the same answer, same response. It will not oscillate, and that is called critical damping. Okay, it is the situation when we have no oscillation, but this voltage will reach its final steady state value in the quickest possible time. If you take higher value of rho, that is say rho square greater than 1, then still there won't be any oscillation, but it will take more time to reach the final value. Okay, so maybe I just draw these cases here. Different possible cases. Number 1, suppose the voltage or waveform reaches the steady state in this way. This we call underdamped response. Then for critical damping, it will be reaching the final value smoothly like this. Then for overdamped situation, it will reach smoothly but will take more time. Okay, this, it will take more time. And for undamped case, it will oscillate possibly for, it will oscillate forever, maybe like this, with constant amplitude. Then the next homework, you calculate the value of this waveform at time 0 plus and at infinity steady state. Okay, and also do the same analysis for current waveform. We have done this for voltage waveform. You have to do this for this current here, this current or this current. Okay, today we shall see one more example. Suppose we have a object with heavy mass, capital M, put on top of a spring with spring constant K, and suppose that I am holding this object with my hands like this, so that this spring is not compressed initially. So I am holding it, and then I will leave my hand, leave the object like this, and then this object will go down and start to oscillate in this way. Okay, and I will also put, say, some damping mechanism, maybe some flaps, okay, so that when this object moves up and down, these flaps experience air resistance, and therefore slowly this object will stop oscillating and settle down to some position like this. Okay, it will settle down as the object in my hand. Okay. Now suppose this position of this object is y equal to 0, and I am measuring y downwards. Okay, and y equal to 0 is the position when the spring is completely unstretched, uncompressed. That is y equal to 0 position. Now this object will move up and down as soon as I leave this object from my hand. So this position y will be a function of time, and I want to know how this y changes with time after t greater than equal to 0. That is the moment when I leave the object from my hand. So that is the task. Find yt for time greater than equal to 0. Okay, for that let me first identify the various forces acting on this object. First of all, we have gravity acting downwards, whose value is mg. Then the spring will impart a force in the opposite direction, and that force will be k, spring constant, let me call it kc, spring constant kc, multiplied with y. Y is the displacement in the downward direction, and then this force will be in the opposite direction, upward. So let me put a minus sign. Next, we will also have air resistance acting on these flaps when this object moves, and that air resistance will be proportional to the velocity of the object, dy dt, multiplied with some constant, call it kd. Let me put a minus sign to indicate that this force acts in the direction opposite to the velocity. So total force in the positive y direction, that is mg, then minus kcy, then minus kdy upwards, kd dy dt, and yes, so these are all the forces. Now this total force should be equal to mass times the acceleration in the downwards direction, d2y dt2. So from this we can write d2y dt2. Okay, this will be, let me bring these terms in the same side. So we will have kd by m dy dt plus kc by m y, and I will keep mg in the right side. So you see that we have a second order differential equation which we can solve provided we have two initial conditions, and let those initial conditions be like this: y0 minus equal to 0. That is because we are leaving this object from the 0 position, and we will also leave this object starting from 0 velocity, y dot 0 minus equal to 0. Second order equation, and we have two boundary conditions, initial conditions. So you can solve it. But I suggest that when you solve it, you first write this differential equation in this way: second derivative plus this coefficient I will define as two rho omega n, and this coefficient Kc by m I will define as omega n square. Then this equation you can write as 2 rho omega n dy dt plus omega n square is equal to mg. Now this equation looks quite similar to the previous problem that we have solved, this problem with this differential equation. So essentially you can use our previous results like this or this to get the y in this case. You don't have to solve this differential equation once again completely. You can use the previous result, but now omega n is defined here, rho is defined by this equation. Okay, so complete it. That is your homework. And these problems, you know, these are quite practical engineering problems. You imagine, for example, an aircraft which has its landing gears, I mean the wheels, like this, and when this aircraft lands on the runway, the moment it touches down the runway, then this aircraft is exactly similar to this system. It has its own weight, these landing gears have some spring, definitely it has air friction. So this aircraft is quite similar to this mass spring damper system that we have discussed now, and except that the moment this aircraft touches down, its velocity is not zero, its downwards velocity is non-zero. So you also have to consider the non-zero initial condition to analyze this aircraft, and it is important to design the different parameters like spring constant, etc., and analyze the aircraft properly, that whether it will have a soft landing or it will have a hard landing and it will hit the ground, or will it bounce back after hitting the ground, or will it oscillate? This you need to analyze properly and accordingly design the different parameters. Otherwise it could be dangerous. Okay, so complete this problem yourself and come back tomorrow.